This video we're going to look at two more tests to determine the convergence or divergence of series. These are the ratio and the root tests. So I've defined both of these right away because I do want to compare. There are some similarities in what they look like, and there are times that we can use either or, and this is true for a lot of our different tests. We have multiple tests available to us, and we can use multiple tests on certain problems. Not every problem can only be solved one way. Now, there are many times that we can't use a certain test on a series, but there are times that we can use multiple, and the ratio and root do tend to overlap a little bit more than some of the others. So first off, let's talk about the ratio test. Let the summation an be any series, and suppose that the limit as n goes to infinity of the absolute value of an plus 1 over an is equal to p. Well then, one of three things must be true. P is less than 1, p is greater than 1, p is equal to 1. So p is less than 1, great, the series converges absolutely. Notice we have those absolute value bars, so we are testing absolutely when we test this. If the p is greater than 1, that tells us the series diverges, and if the p is equal to 1, the test fails. We would need to find another test. The root test, let this summation an be any series, and suppose that the limit as n goes to infinity of the nth root of the absolute value of an is equal to p. Again, the three cases, p is less than 1, p is greater than 1, p is equal to 1, and the same three statements are true. P is less than 1, the series converges absolutely. The series diverges if the p is greater than 1, and if p is equal to 1, the test fails. So in both those third options, we can see these tests can fail. We won't know that till we run the test. And so whenever we're testing our convergence and divergence of series, we're having to start with a little bit of a guess. We've talked about some things that make it easier to see which way we might want to go, and we're going to see those in these two tests too. But there are times that we think we're going to choose a certain test and it just fails, and we have to move on to another test, and that's fine. That's what we have to do. The nice thing about both of these tests, there are no initial conditions that have to be true. Notice it says let an be any series, the summation be any series. So it's not like the integral test where we have to have positives or have to have certain conditions to meet. Same thing with comparison tests. So let's go ahead and do some examples. Let's take, for starters, the summation n is equal to 0 to infinity of n factorial over 5 to the n. Now, I see that there is an nth power, and a lot of times the nth root of the nth power, well, all the time that will get rid of it. So that could be a useful step. However, I have this n factorial as well. So n factorial, remember, is n times n minus 1 times n minus 2 times and so forth. And so I'm just a little bit worried, or my concern is that when I take the nth root, that might not help me with this much at all. It might. So in this case, I would probably lean towards a ratio test. Anytime we have those factorials, the ratio test can be a good place to start because it does allow us to eliminate the fact that we have infinite, or not infinite, I shouldn't say that, but with these multiplications of n all the way down to n to the times 1. So the ratio test can be useful. Now, actually, the root test can actually simplify that a lot of times too, because we're still doing division. Or we can be applying the nth power in some cases. Just a lot of times I will default to that ratio test. So let's see what happens. We're going to take the limit as n goes to infinity of the nth term would be n factorial over 5 to the n, but I really need that to be the n plus 1. So we're going to have n plus 1 factorial, and 5 to the n plus 1. We have to take the n plus 1 case first, and from there I'm going to divide it by the an, which is just the n factorial over 5 to the n. And notice I have that in absolute values. Now, we have a fraction and a fraction, so I'm going to multiply by the reciprocal just to make it look a little prettier. We'll have n plus 1 factorial over 5 to the n plus 1 times 5 to the n over n factorial, all inside the absolute values. So n plus 1 factorial, remember what that is telling us is it's n plus 1 times n times everything less than n, or we could write that as n plus 1 times n factorial. We can just factor off that first n plus 1. And then 5 to the n plus 1 is 5 to the n times 5. So notice the n factorials will cancel, the 5 to the n's will cancel, And so we're left with here the limit as n goes to infinity, the absolute value of n plus 1 over 5. And so if we were to now try to evaluate this limit, it's very easy because we don't have those factorials and we don't have the 5 to the n's to keep track of. We're just plugging in infinity plus 1. That's clearly going to infinity, which is greater than 1, which tells us this diverges. So again, we still want to use our words to tell what we're doing. So we took our original problem, we took the series n equals 0 to infinity of an plus 1 over an, and we know this diverges using the ratio test. So always state what test you're using to reach a conclusion, because that p was greater than 1. That tells us it diverged, and we were using our ratio test. Let's take another series. Let's go from n equals 0 to infinity, n plus 2 over 2n plus 7. And so this is another good case, I think, for the ratio test because we have some fractions already, and we can see, like we did before, fractions divided by fractions, sometimes will simplify, will become a little bit nicer. I don't think I'd want to use a root test here. I don't see any advantage to using a root because I don't have that nth power under or inside my series. So the root test doesn't really seem like it would apply much. Let's use our ratio test. So I'm going to take the limit, n goes to infinity, n plus 1 plus 2, because we have to start with that n plus 1 case, and we'd have 2n plus 1 plus 1. That was a 7, actually. Sorry, I can't read my own writing. Not that it really makes any difference, just a different constant. Divided by the original case, n plus 2 over 2n plus 7. That's all in the absolute values. So I'm going to do two things in one here. I'm going to simplify. So we'll have n plus 3 over 2n plus 2 plus 7 is 9. Times, I'm going to multiply by the reciprocal, 2n plus 7 over n plus 2. That's all in the absolute values. So if I want to take this limit, I can probably see where it's going by now, but if we can't, it might be a good idea to multiply it out. So we'd have 2n squared plus 6 plus 7 is plus 13n plus 21 over 2n squared plus 9 plus 4 is plus 13n plus 18. So notice the factors weren't the same, they weren't going to cancel, no factors canceled in this line right here. And once we multiply them, we can very clearly see that the degree of the top matches the degree of the bottom, that if we were to plug in that n going to infinity, we would have these two dominant terms, they're both going to 2, so we'd have 2 over 2, which is equal to 1. And remember what that tells us, this case doesn't tell us anything, it's inconclusive. So we tried the ratio test because we said, hey, it's a fraction. Ratios can work with fractions relatively nicely. It simplifies some things sometimes. However, we got that p is equal to 1, and that told us the test was inclusive. And so now I need to go back and think of another test. And remember, the easiest thing I said to always try first is the nth term test for divergence. Always easiest to start there. So really, I would never have started with the ratio test other than I want to show you an example of something that was inconclusive. Let's see what happens if we were to apply the nth term test. Nth term test says let's take the limit as n goes to infinity of n plus 2 over 2n plus 7. That is going to a 1/2, which is not equal to 0, and so that tells us conclusively that the series is divergent. Series n equals 0 to infinity of n plus 2 over 2n plus 7 is divergent by the nth term test. Always start with that nth term test, unless it's a geometric series, and unless it's something you look at and know right away it's going to converge. Start with that nth term test. It's going to save you a ton of time. Here we can see clearly it was going to be faster than the ratio test, even if the ratio test had given us a result. It's only 2 lines versus the 1, 2, 3, 4, 5, 6, whatever it was above that we spent. But then too, if another test fails and the divergence test would have worked, that's clearly the fastest thing to do. Let's do some other examples. Let's take the series n equals 1 to infinity of negative 10 to the n over 4 to the 2n plus 1 times n plus 1. And notice I've changed around the indices a little bit. I think I had 0 on the last one, 0 on the one before, and then n equals 1 on this one. I've changed it around because it didn't matter. Remember, it said let it be any series, so it doesn't matter where it starts, ends, anything like that. We're just applying these two tests to whatever we have given. So I'm looking at this. I see some exponents again, so maybe I could use the root test in an effective way. The fact that the roots aren't the ratio, rather the exponents aren't the same, that's going to be a problem, I think, when I come to the root test. And then also the fact that this doesn't have the exponent isn't a deal breaker, but again, it's leading me to believe maybe I'll stick to the ratio test. I think the ratio test might be a little bit easier on this one. We will see some examples of the root test, I promise. Let's do one more with the ratio. So the ratio, we're going to take the limit as n goes to infinity of negative 10 to the n plus 1 over 4 to the 2 times n plus 1 plus 1. And we'd have n plus 1 plus 1. And that's going to be divided by the original, negative 10 to the n over 4 to the 2n plus 1 times n plus 1. So let's see what we can do with this. So we'll have negative 10 to the n plus 1 over 4 to the 2n plus, that'll now be a 3 times n plus 2 times, and then the other fraction, for to the 2n plus 1, n plus 1 over negative 10 to the n. So like we did before, let's kind of break these things up. This negative 10 to the n plus 1 is really negative 10 to the n times the negative 10. Because remember those exponents, we can just break them back apart into the multiplication of like bases. And then the 4, same story, we can write that as a 4 to the 2n. And really I want to compare it to a 4 to the 2n plus 1. And that means we had to have a times 4 times 4, or times 16, 4 squared. Because when we multiply those like bases, we would add their exponents. And so we'd have 2n plus 1 plus 1 plus 1. That'd give us the 2n plus 3. So we can see some cancelization here. These cancel. And then the 10 to the n's, negative 10 to the n's cancel. And so let's see what we're left with. We have the limit as n goes to infinity of the absolute value of, we have a negative 10 left on top. We have an n plus 1 left on top. We have a 16 and then an n plus 2 left on the bottom. If we were to take our limit, we would have the negative 10 just becomes a positive 10 over 16 because the degrees of both top and bottom are the same. So we get 10 over 16, which is less than 1. And remember the ratio test, if it's less than 1, tells us it does in fact converge. So the series summation n equals 1 to infinity of negative 10 to the n over 4 to the 2n plus 1 times n plus 1 converges, and it does so absolutely using the ratio test. Second, use a ratio or a root test. It has to show that it converges absolutely. If it converges, if it diverges, right, or if it's inconclusive, we don't know. But if you're using the ratio or the root test to show convergence, it must converge absolutely. Now, also remember, we are not saying here that the sum is equal to 10/16 or 5/8 if we want to simplify it. The test is just testing whether it converges or diverges. We are not finding its sum. We have not found its sum. All right, let's move on to another example. I told you I'd show you a few with the root test, so we'll talk through what may make the root test a little bit better in these cases. So we have an n cubed on top, and we have a 2 to the n on the bottom of our series, and I should give it some an index, so we'll go from 1 to infinity. It needs to go to infinity, otherwise it's finite, and we can definitely find its sum. But the index doesn't matter. So here, let's think about why the root test might be appropriate. Well, once again, we see that we have that n in the exponent. We have an exponential function in the denominator. Unlike some of the earlier ones we did with the root, we don't have any exponential. Exponentials can be challenging in roots. And we don't have different exponents, which also, again, might be challenging, or maybe easier, I should say, to use a ratio test. So because I see that exponent, I'm thinking, well, maybe the root test is a good place to start. I should also note that on all of these, I've ignored the divergence test just because I do want to show the test regardless of what actually happens to the sequence. But this one does, in fact, go to 0 if we're to take the limit as n goes to infinity of n cubed over 2 to the n. That would be 0. So I'm being a little bit sloppy because I just am trying to illustrate the test. It is always a good idea to start with that test for divergence because that'll find divergence much faster than anything else. Okay, so we know that divergence test fails. We'll go to look for something else. We're thinking we might want to use the root test. So the root test says take the limit as n goes to infinity of the nth root of the absolute value n cubed over 2 to the n. Now if n is going to infinity, we can just drop those absolute values, just deal with the positives. But we can see that we're going to have n to the 3 over n over 2. Remember, we can always think about exponent as these roots as exponents. And so n was raised to the third power, and then it's to the 1 over n power for the root. 2n, when we take the nth power of that, it is just 2. So now we need to find this limit as n goes to infinity of n to the 3 over n over 2. Clearly over 2 not a problem. What I want to really concentrate on for a minute, let's just break it off in its own problem so we don't get too confused. Let's look at this n to the 3 over n, because this is an indeterminate power. We have infinite being raised to a 3 over an infinite. So let's rewrite this using our logs. And so I'm going to create a base of e and then raise that e to the natural log of n to the 3n power, which allows me to bring that exponent down to the front. And so now I'm going to have e to the 3 natural log n over n power. And this thing is going to infinity over infinity, which tells me I can use my L'Hopital's rule. So we would have 3 over n over 1 when we take the derivative of top and bottom. And as n goes to infinity, this thing is going to 0. So we'd have e to the 0, which is equal to 1. So now we can come back here to the original limit, and we know that this is equal to 1 over 2, or 1/2. That is less than 1, and so that tells us that this does, in fact, converge. So we can state that the series n to the third, 2 to the n, over 2 to the n, from n equals 1 to infinity, converges, and again, converges absolutely using the root test. Root and ratio test will always show us convergence by an absolute measure. And then let's, just for the fun of it, flip that over just to give us another example. Let's take n is equal to 1 to infinity of 2 to the n over n to the third. The root test worked so well in that last example, so why don't we use it again? So let's take the limit as n goes to infinity of the nth root of 2 to the n over n cubed. and we need to take the absolute value of that, but like I said before, we can drop the absolute value because the rate is going to be positive if n is going to infinity. And so we'll have 2 over n to the 3 over n power. Remember what we just saw a second ago is n to the 3 over n is simply equal to 1, so we get 2 over 1, which is 2. That is greater than 1, which tells us that this must diverge. Now, once again, I skipped the easy thing. I told you just a few minutes ago that it is much easier to start with a test for divergence. And what we had just found a couple minutes ago when we did that n test for divergence is that n cubed over to the n, if we take the limit as n goes to infinity, that diverged. So that had the potential to converge. I said that exactly wrong. N cubed over to the n, that went to 0, meaning that the series had the potential to converge. Well, if it's going to 0 and we flip it over, then we have a 0 in the denominator. That tells us that this has to be going something to other than 0. So it would have been much, much faster to use the nth term for divergence here. This is going to infinity. So that would have been a one-step process, but we'll just rely on our result from the root test. We know that the summation to the n over the n cubed goes from 1 to infinity, must diverge using the root test. But again, could have used multiple tests. We could have used that nth term test for divergence, and there are other tests that may have worked still. So there are multiple tests that can work on a given problem. We have multiple tools, multiple skills at our disposal. So it's a matter of looking at which one do we think will be the easiest, and then once we get into it, will this test actually work or does it fail for some reason? We're going to see a few more tests in the upcoming videos, so we're not quite done yet, but we're getting close to a pretty comprehensive list of tests.